We are really starting a little bit slow. Sometimes, as you might face when you read the material, sometimes it's a little bit difficult to capture the concept. But if you read a couple of times, you should be able to discover the essence of especially MPP approach. I haven't talked much about the MPP, but the handout, the file I gave you, the second file is MPP based the method, which is identical to FOSM or SO RM is all same. MPP really means the most probable point. That's what we are looking for. The concept of solving the structure reliability problem is using the simplifying approach to really locate the most probable point. That's the approach we're gonna really looking into it. So as I mentioned, I'm not gonna giving you additional handout. I have my own lecture note. Really take them out from the two references I gave you. So, but we have to capture the essence of it, and otherwise it's simple. We're gonna do first order, reliability. First order reliability method. I'm gonna, even if it's some statements, I'm gonna write it down, some important statements, consequences I'm gonna write down for your review. So this is FORM. First order. We are using the performance function or limit state function, then expand into the first order of Taylor series. That's what the first order really means. So here, as I wrote the Monday, the problem to solve, we wrote a few times already, which is a probability G X. This is the multi-dimensional the variable, random variable, is less than equal to 0, or this is integration minus, well, not minus, the region. This is the region, so I can say G X less than equal to 0, Fx, simply speaking, this is a compact expression, and this is of course multi-dimensional. That makes the whole story solution very difficult. But it happened not only for structure reliability, for any field, you face always, as I mentioned, the coupled equations of motion to solve. And as I mentioned Monday, then you cast into the so-called modal space, transform into modal space to decouple the equations of motion, then solve the whole bunch of 1 degree of a freedom model. That's the that structural dynamics idea. Here is very, very close. So this is all coupled equations of motion. This is all coupled. Well, this is all coupled because x here is xi, I is equal to 1 to all the way through the n coupled equations. And so the whole idea is we want to throw into the standard normal space that we can handle comfortably and easily. And of course, one of the assumptions we made here, all this is the mutually exclusive each other, such that the random variables are assumed to be independent each other to make the life easier. Then, as I mentioned the other day, what happens if it's a correlated situation? So I'm not sure whether this author really handled in the last minute the coupled random variable, the cases, but regardless, we have to throw into the space, then all the random variables are independent each other, whether it's a correlated or uncorrelated, then try to solve the problem. That's the approach we're going to take it here. And sometime next week, I'm pretty sure we can start solving simple example problem, then getting into the harder. Then I will assign the really term project problem, which you will formulate and solve. That's the directions it's gonna go into. The difficulties, I'm gonna summarize difficulties. To direct the difficulties to solve PF equation, above equation, directly. But nowadays, all today's computer capability wasn't good, but nowadays this computing capability is excellent. Even our HPC is superb. From the size of the OSE faculties and students, we discovered, we found our HPC high performance computing facility is far better than Kim here, the 기계연구원 Kim, much better. We check out the speed and all that, at least to solve particular engineering problem, complex problem. It can handle compute 5 times faster than their computing system compared to our computing system. First would be the probability function is multi-dimensional problem. This is a problem. If it is one or two-dimensional, you can handle beautifully. We have done that all by looking at all different introducing probability models and all that. And two, fx is not nicely linear, is non-linear. It's not piecewise linear, it's non-linear. But using the Taylor series expansion, you can make it piecewise linear. Lots of situations to solve engineering problem, you can cast a non-linear problem into piecewise linear. You can solve by segment and use summation. Another problem is GX. GX is a performance function. Okay. For example, GX for two-dimensional, what we did was GX is like R minus S. We are familiar with R minus X. That's like a GX. Or we use two different names, but it's all the same, performance function or limit state function. Or performance function. And GX is concerned, this is the really boundary, the boundary that two different regions are separated. One boundary is a safe region, the other boundary is a failure region. So GX is equal to 1 is of course is multi-dimensional, and also nonlinear. It's a problem. So there is a problem, especially for engineering problem. Is more higher level nonlinearity could be involved, higher multi-dimensional situations arises. So it is a problem. So engineer can survive with around 5% error. A physicist, they can't survive 5% error. It's impossible. So they have to go down 0.001. For us, it's meaningless for engineers. But for the physicist, it is not acceptable. So for the first order reliability method, first thing to do is transformation. transformation of one space to the other. So I'm going to call that transformation from X space. This is all coupled space into the U space. As you hear my lecture, I demand you really read, sit back and read the two references I gave you. I demand you must read slowly, okay? My pace at the beginning always slow, captured the concept. U space. And U space is standard ALD, normal, probability. Space. U space. Over here, U is random variable. Capital letter is, of course, is multi-dimensional. For the X space, is simply the X random variable is equal to Xi, I is equal to 1, 2, all the way through N variable. N could be 10 or 20 or 30 and whatever. And from here to here, U space is standard. When you hear about the standard normal probability space, you already look at that sort of the normal, standard normal probability function, right? Phi. So this I use as the distribution function, and maybe we can use like this guy as a U as a density function. And for the standard normal probability density function or distribution function, we know the mean is equal to, and standard mean is equal to what? Say 0, right? 0. And of course, there is a standard deviation. Standard deviation is equal to 1. So here we are dealing here for the 1D, we are dealing with the 0. This is like x. This is like fx. We are dealing with mu x is equal to 0. But standard deviation, I'm going to say, is like a 1. So when you hear about the throw transform from X space into the standard normal probability space, that's what you have to keep that in mind. So this is the first kind of the approach or steps to looking into it. And he put the name as a first step. And simplifying name, if you want to put the statements, simplifying integrand. integrand means is really fx. This is an integrand. Integration of multidimensional probability density function. So how are we going to simplify it? So simplifying integrand, the idea is, first idea comes transformation. So this is like, I'm going to put the A, and B is, I'll write it down even if it's a little bit not long. Transformation before I write this guy, I'm going to say f xi xi. This is a random variable, capital Xi, because it has n different, the random variable is equal to phi ui. If I write the random variable here, it should be like a ui. Probability distribution function in the X space is equal to transform into the standard normal, the probability space, which is a U space. So here is a U space, U, which is as I write over here. And this is X space is Xi dash space. I'm going to make the statements over here. Transformation from X space to U is based on the condition that on that cumulative distribution function, we use a CDF, right? Which is simply capital Fx. Cumulative distribution function of random variables remain same before and after the transformation. Before transformation, which is capital Fxi, and after transformation is phi ui. This is like a Rosenblatt transformation. Rosenblatt. But right now, what FORM really assumes, as I talked it already, if this follows if this follows the normal, this follows the normal. Of course, in this phi here, just as a reminder, I'm going to drop the subscript. If this is a phi x, we know this is equal to, for the one-dimensional, is 2 pi minus infinity to x e to the minus t squared 2 dt, standard normal distribution function with mu x is equal to 0 and the sigma x is equal to 1. So from this transformation, this is the Rosenblatt transformation. The reference is the paper is listed in the last page of handout, published in 1972. And from that transformation, I can say that UI from here is equal to phi inverse f xi bracket. This is from here, right? So inverse is as a notation wise, but this will get clear. This phi ui is inverse of fxi. For example, let's say x1, if x is equal to normally distributed function with the mean and the standard deviation, then using the transformation here, I'm going to simply drop the I to say say u is equal to phi inverse f x, which is equal to phi inverse, and this is back to Rosenblatt transformation, which is equal in both the space for CDF. So I can say this guy is equal to the phi and sigma x minus mu x, phi inverse, then phi, then it's back into the sigma x minus mu x. So if I reset u is equal to that, then just to rewrite this guy here, x is equal to mu x plus sigma x times u. So as you look at this x variable in x space and u variable in the u space, so this is really, can claim this is a linear transformation. So which is really nicer. Okay, then now we can work on the U space. Now you can work on the U space. So now, now I can say that now, so I can say G, we use a Gx is equal to 0 in the X space. Some of you could say, geez, what the hell is he's talking about it? Simple transformation from X space, real world space, into U space, which is a dream world space. And in the dream, you can really do anything you want to do and throw back into reality. Then you solve the problem set. So here, this is that, but in the U space here now, apply the transformation. I can say now everything is in U space. You could use H, which simplifies is simply functional relation. So we're gonna just use the same G, which is just a function of U. And here this is gonna be U space. Otherwise, two different functional notation, and that's immaterial. We can just use the same G for the simpleness. Then I can cast the probability of the failure in the using the U space variable, not the X space variable. I can say this is probability such that GU is less than equal to 0. We are in the U space, dream space, okay? So, which is now is integration. So it's a GU, same thing, identical, less than equal to 0, reintegration region. And phi, I can say U, X, this is U. Rather than integration in X. In the U space, think about the standard normal distribution, like this. Now you can turn this guy into the 3D, like a U1, U2 space. In the U1, U2 space, now you can make a projection. So it's going to be a volume, right? It's going to be a volume. So project this contour. This is this is Fx or Fu. This is Fu because mean is equal to 0. Sigma x is equal to 1. When you throw the contour down the surface, what kind of the contour shape do you anticipate? It's a circle, whole bunch of circle, right? For the X space, it's not circle. It doesn't have to be circle. But in this case, everything is all simplifies it. And if you cast into the U1, U2 space, this is origin, and all that contour you can throw as concentric circle. That makes a lot easier to identify so-called most probable point. So this is because of that simplification. So here, this guy, U is equal, I can recast this into the multiplication of if you look at the book, it shows just like this. And if you there is a condition that this phi, small phi u, is equal to multiplication of this guy. This guy is like a u phi maybe ui. There is a condition. What condition is this? This is a normal, standard normal. Standard, not only standard normal, however, condition for xi are independent, ui are independent. Whole thing f, something like this, can be cast into the multiplication f2, whole bunch of multiplication, right? When it is independent each other. For the joint x2 is equal to x1 multiply x2. We look at it. That's only good when the random variables are exclusively independent each other. You can simply change into multiplication like this. So that's why this is simply pi. No magics, okay? So here this is really the standard normal probability density function. But one thing I want to do to avoid any confusion, I'm going to put this guy here. This is standard normal density function, and this is going to be repeat n times with I is changing from 1 through n. So if you do that, I can rewrite this guy into the slightly different forms such that this is equal to 1 over square root of 2 pi n power, okay, and exponential function minus half summation I is equal to 1 through n u I square. So there's n power here. Or you can rewrite this guy as 1 over 2 pi n power, then exp. If I write over here, this is 2 times d square. Over here, d square is equal to u1 square plus u2 square all the way through un square, which is simply as I write here, as I is equal to 1 through n ui square. So d is square root of ui square, and this is simply nothing but the norm of the u. So over here, u is equal to ui, I is equal to 1 all the way through n. Okay? So this is really norm. You will see better meaning as we proceed the lectures here. And this d is equal to summation of ui. That I think we have to. So step 1 is it's a little bit simplification to make easier to solve the problem. But when you make an assumption for any situation, you have to be careful whether it is meaningful or meaningless. Sometimes mathematician and researcher. One time we have 2.5 years ago, there was a really wonderful scholar who visit here to really propose the approach to solve complex fluid problem. I'm not really accusing him, no. And he put out the equation set like this, PF, probability of the failure, PF. Gosh, it's multidimensional, everything's all nonlinear. Then he said, okay, here is a way to solve. This was exactly the way I do here. Make assumption, careful. Make another assumption. Make another assumption. Why? To be able to solve using the tools which are available in our pocket at the present time. The one thing I'm afraid is by making multiple assumptions, you are end up solving totally different things. Has nothing to do with the original physics of it. You have to be very careful for your thesis research work to be able to solve for the nonlinear problem. You get down to the piecewise linear problem. You have to sit back, is it okay or not? If it's not okay, piecewise linear may not work. So for this sort of the problem is part of the optimization problem. Optimum. And you have, multiple peaks, then you're looking for this, but you might end up, your algorithm found that peak and masked by the many different reasons. Oh, this is what I'm looking. Then this is the answer I got. Wrong. Your peak is way out there. In the search algorithm, we're going to talk search, MPP search algorithm, we have to make sure. If you get closer and closer to your eye, you don't see any other peaks. Maybe peak may be way out there. You don't see such a monster growth peak, but you may hung up here. Approximation, very useful tool, but shouldn't distort the result in there. So now I can overall express the PF nicely. This is a PF, I keep reminding PF. This is a destination we are heading. One way or another, whether you simplify or not, there's assumption. What was the one of the assumption I had already? Assumption. Mutually exclusive, right? We already made a commitment. Assumption. Mutually exclusive. Correlation function is equal to 0. There is no covariance assumption to be able to solve multidimensional problems. Okay, it's okay. So we'll think about the correlation later. That's what the thing is. PF is equal to, it's a back to original thought. I don't want to just showing the result we got from to the last minute, but always look back, and this is what we are looking into. In what space? What space? We are still in the U space. It's perfectly okay to investigate the probability of the failure. And here, this is a pi rewrite, okay? I is equal to 1 through n, and equation set is 2 pi, same thing here. Exponential function minus half of the ui square, and du1, du2 all the way through dun. That's what we are solving. But I clearly want to indicate this guy is like that. Otherwise, got the impression that this is only 1 over square root of 2 pi, but in fact, when you put it out there, it's going to be this 1 over square root of 2 pi to n power. So when you draw this guy into the 3D space for the U1 and for the U2 only, that's all we can show in the 3D space we are living. So as you see, if you look at the notes of book, it lifted up to here, reset. Then it has right? So that's what you have. As I mentioned, it's just to look at the projection. That's what we had. In reality, the whole thing, this should be touched down on the baseline, right? So remember. So here, the projection of all this isocontour should be nicely circled. Very nice, very powerful to solve the problem. This is really simplifying to solve the problem set for the PF. So you can take a look at. So in like you, the file number 1, handout number 1, you see this is different. This is my lecture notes, which I prepared. You see this problem is 7.4. If you look at there, this is all a circle, right? Is this circle center is origin. You have your notes, your lecture, the handouts. Center is right here. And this is really for what region? Failure region. And what's this? GU is equal to 0. This is U space, okay? So GU is equal to 0. And this is the PDF contours is all there. This is 0. And this region is a safe region, right? GU is greater than 0. Identical format, but still easy to solve because it's in the normal, standard normal probability space where all the circle comes right in. Okay, I think I'm gonna stop right here, and Friday we're gonna do the step 2. Step 2 is simplifying the GU function. So step 2, we're gonna look at simplifying the G function. We'll look at the GX, of course we'll look at the GU. Then we can introduce the Taylor series and talk about the expansion point and how to get to solve the PF, really solve the PF. This is one step, simplifying step. Second is massaging the G function to get down to the probability of the failure. Okay, so I'll see you Friday. And read, okay? So the 2 files, if you look at one, the reference and second reference, 90% identical. Notations are slightly different. But it's good to read both references. I'll see you Friday.